Hi, my name is Carolina and I'm here for another experimental demo.
Yes, today we're going to show you the principles of optics, both refraction and reflection. And for that purpose, I'm including some diagrams along with this demo that you will have in the menu items for Blackboard. But in the meantime, we have what's known as a 5-ray laser box. It puts out 5 laser beams, if you want to call it, or rays. They're parallel to one another, and they mimic the sun's rays or rays coming from stars. Anything that's far away, the rays are essentially parallel, as shown in your textbook. Now, what we're going to first do is use a block of plexiglass to demonstrate how light refracts or bends as it goes through this clear material. It could be glass. We have plexiglass with magnets on the back. So what we're going to do is place this at an angle in the beam, and we're going to rotate it a little bit, and then we're going to a little bit more, I think will be good there, and then we're going to turn the lights off so that you can see this. As you can see, the rays of light are going directly through the block of transparent material, but they bend as they enter. The light is coming from the left. It bends at an angle as it enters. Some of it actually reflects a little bit, as I can see, but when it exits the plexiglass, it goes back to the same direction. It bends again back to the same direction that it was originally going. Now, if Carolina will tilt that a little bit, you'll see as she rotates it, as it nears vertical, that has internal reflections too, as we can see. Look at that. We didn't expect that. That has internal reflections. And depending on the angle of the transparent material, depends on the angle the light comes out at. If you compare the angles as a ratio, you get what's known as refractive index. And refractive index, or the amount of bending of the light, is found in gemstones. Diamond has the highest, by the way, of any of the natural gemstones. And eyeglasses have refractive indexes, and we use this to bend the light to change the direction of light, which is the field of optics. Now, if we can have the lights once more, we're going to get rid of that one. We're going back and forth between lighting and no lighting. We're going to put that one down. Now we're going to use a double convex lens. It has a positive curve on both sides. That's why we call it a double convex. And we're going to put that at the beginning of the beam. Right there, a little higher, and that's it. There we go. We'll get the lights so that we can show you this. Notice that the curved sides of the lens focus the beams down to a point, which we call a focal point, right there. And then they diverge again as they go through the focal point. The focal point is where the image, if this was looking at a star, would appear. In fact, this is a very simple refracting telescope. The lens is called the objective lens, and the focus is the little where the rays come together. The distance between the lens and the focal point, or if you treat it as a plane, the focal plane, is where the images appear and is known as the focal length. Refracting telescopes usually have pretty long focal lengths, on the order of 1 meter to 20 or 30 meters on the biggest telescopes. So now we're going to go back to lighting, and we're going to progress to the next type of lens, which is called a concave lens. Both sides are inward, not outward. And when we put a concave, this one's double concave, so it works even better in the beams right up there. We're going to get the lights. You see this a little better. Yeah, look at that. The double concave, cave means in. You can always remember it that way. The double concave lens spreads light out. It disperses light. If that was one solid beam of light from a flashlight, it would disperse the beam out. And can you use a convex lens with it? Let's try it. Let's take the convex lens and put it right in front, ahead of. Yeah, let's see what happens. It starts diverging and then converges. Let's move that double convex lens in and out a little bit. Maybe not that one, not that's this one here. Move it in and out. See what happens. It changes everything. Move it towards the right. Look at that. So it really does change how things work. Okay, we can have the lights now, and we're going to go to reflection. In the case of reflection, light bounces off a surface, a mirror in other words. Here's a plain flat mirror. So what we're going to do is put it into the 5 rays of light, and we're going to get the light so you can see this better. You can already begin to see it. Look at that. As each beam of light hits the mirrored surface, it bounces off like a billiard ball off the side of the table. And she can adjust the angle. If that angle is 45 degrees, let's make it 45. Yeah. The light hits it at 45-degree angle, the mirrored surface, and it bounces off at 45 as well. And that's known as angle of incidence equals angle of reflection. Let's see if we can make it go straight up. Look at that. Keep going. A little bit more. Look. We're going to leave it there for a second. The light beams are hitting the mirrored surface at 45 degrees and they're bouncing off at 45. And they go straight out. This is how a Newtonian telescope works. It's got a little diagonal, it's called. It's a little diagonal mirror. And as the light hits it, it bounces off. In fact, let's take the double convex lens, which we'd have in a telescope, and put it in front of the box. Oh yeah. Now, let's move the 45-degree angle mirror a little closer to the light box. There we go. Oh, go a little to the right. Right there. Right there. In come the rays of light through a objective lens for a telescope. They hit a small diagonal, and as they bounce off, they come down to a focal point where you put your eyepiece and you can see the images. Did you know that? You're taking a picture of it with your cell phone. You're so cute. But that's how...
Looks cool.
Yeah, it's how a telescope works. The reason you bounce the light off to the side is so that it's more convenient to look through the instrument in that fashion. So let's get rid of these lenses. And we don't even have to... yeah, let's go get rid of those, and we'll go back to the last one, a curved mirror. The curved mirror, one side is curved and it's silvered. It's got aluminum on it. So let's put that in the beam. Oh yeah, over to the right a little bit more. And now we can get the lights, and we're going to play with that one. This is how a reflecting telescope works. Notice that the beams hit the mirror at different angles. The one in the middle, called the optic axis, hits straight on at 90 and it bounces back at 90. But the others all do a little differently. The light bounces back to the point in the center, which is, guess what? The focal point. That's how it works. If we had a small flat mirror, we would put it right in there and bounce it out to the side, because it's hard to put your head there in the middle of the telescope. Yeah, it's too big though. That's the only problem. And let's turn the primary mirror, which is what the mirror of a telescope is called. Look at that. Let's bring it down a little bit. A little bit more, a little bit, right there. Now what you're doing here, this is known as a Scheibenspiegel telescope. The light hits the mirror at an angle and then it bounces out to the side of the tube where you put your eyepiece. Isn't that neat? Actually, you put another mirror there and bounce it back where you put an eyepiece. It's what we call folded optics, or catadioptric type of telescope. So as you can see, there's a real varied number of ways that you can change the direction of light, either by bending it as it goes through a substance known as refraction, or by bouncing it off or reflecting the light off of a surface. And Carolina is really playing with this thing. You can put anything you want here. You can put, just see what you get. Look at that. Look at the infinite number of combinations you can get. And I don't know what that instrument could be used for, but it's yeah,
cool though.
It does look cool. Yeah, it does. Yep. We're going to get the lights back on, and I'm going to thank you for assisting with this demonstration. And I'm going to put some materials for students to answer in this particular demo itself. Again, thank you.